Good day, everyone. I'm delighted to welcome you all to our sharing sessions on ODE, that is Ordinary Differential Equations, or my name is Di Wei, and we will have two speakers with us today. They are Xuan and Jia Ze. So, in this video, we will dive into the fundamentals of ODEs, their importance, and their wide-ranging applications. Guys, do you know what is ODE? An ODE is an equation that relates a function to its derivative. It describes how a particular quantity changes with respect to another variable, typically time or space. Do you know? Ordinary differential equations are crucial in mathematics and many other fields. They help us model and understand some phenomena such as population dynamics, heat transfer, motions of objects, electrical circuits, and so on. By studying ODEs, we can predict and analyze how this system evolves over time. ODEs are widely used in engineering, physics, biology, economy, and many other disciplines. For example, they are essentials in designing control systems, modeling biological processes, and predicting economic threats. Now, I'd like to invite our first speaker, Xuan, to explain this concept in more detail and provide some illustrative examples.
Thank you. As mentioned, the order of an ODE is determined by the highest derivative present. For example, in the equation y double prime plus y equal to 0, the highest derivative is y double prime, making it a second-order ODE. Linearity refers to how the function and its derivatives appear. If they appear to the power of 1, it's a linear ODE. Otherwise, it's non-linear. For instance, dy over dx plus y equal to 0 is linear, while dy over dx plus y squared equal to 0 is non-linear.
Alright, thank you for explanation. Now, let's move on to understand the importance of initials and boundary conditions in solving ODEs. The initial conditions provide specific value at a certain point is essential for obtaining the unique solution. For the boundary conditions, it specifies values at the boundaries of the domain crucial for solving physical problems where the edges or starting points are not. So, to give a small context, our second speaker, Jia Ze, will share some examples and applications where these conditions play a crucial role.
Absolutely. Consider Newton's law of cooling, represented by the ODE dt over dt equal negative k, T minus TA. Here, T is the temperature of an object, TA is the ambient temperature, and K is a constant. Solving this ODE with an initial temperature condition helps predict how the temperature changes over time. Another example is logistical model in population dynamics, which use initial conditions to predict population growth.
Oh, so thank you for those insightful examples. Next, let's explore different methods for solving ODEs. There are several techniques for solving ODEs, including the separations of variables and integrating factors. Let's start with the separations of variables. This method is useful for first-order ODEs. For example, consider dy over dx equal to ky. We can rewrite this as 1 over y dy equal to k dx. We integrate both sides and find a solution for y equal to c exponential power to kx. The integrating factor is helpful for linear first-order ODEs. For instance, in dy over dx plus 2y equal to 3, we use the integrating factor exponent power 2x to transform and yielding y equal to 3 over 2 plus c exponent power negative 2x. What? You don't understand? No problem. Let me teach you step by step. But due to the time constraint, we will just show the step. Now you get the answer. Let's hear from our first speaker, Chuan again about another method, like the methods of undetermined coefficients and the variations of parameters.
The method of undetermined coefficients is used for non-homogeneous linear second-order ODEs, such as y double prime minus 3y prime plus 2y equal to exponential power to x. We find the complementary function and a particular solution to form the general solution. So here are the steps, but also due to the time constraints, we just show all the steps to you guys. This is step 1, find the complementary function. Next. Step 2, find a particular solution. Next. Okay, next. Yeah, this is step 3, form the general solution. Okay. So, variation of parameters, on the other hand, is used for solving non-homogeneous linear ODEs. For example, y double prime plus y equal to tangent x can be solved by assuming a particular solution, form and solving for the parameters. So we also will show the step. Step 1, find the complementary function. Next. Step 2, find a particular solution. Next. Step 3, use the method of a variation of parameters. Next. Next. And we will find our general solution.
Whoa, excellent explanation. Now, let us look at some numerical methods for solving ODEs, such as the Euler methods and the Runge-Kutta method. The Euler method is a straightforward numerical technique for first-order ODEs. We use the formula to iteratively approximate the solution. For the Runge-Kutta method, particularly the fourth-order method, RK4, is widely used for its accuracy. It involves calculating intermediate slope, its k-values, and combining them to find the next value in the solution. ODE have numerous real-world applications, including electrical engineering, such as RC and RLC circuits, population dynamics, such as logistic growth models, the predictor-prey relationship, Lotka-Volterra equations, and modern technology such as machine learning and AI. Now, let us invite our speaker to Jia Ze again to share with us for the real-world applications of ODEs.
Thank you, Di Wei. Firstly, I will talk about the exponential growth. Consider the ODE for exponential growth or decay is dy over dx equal to ky. This model processes such as population growth, radioactive decay, and interest calculation. We need to find the solution to the differential equation. Given the initial condition y0 equal y0, we separate variables and integrate 1 over y dy equal k dx, leading to ln modulus y equal kx plus c. Exponentating both sides given y equal y0 exponent power kx, where y0 is the initial value. These models can describe how a population grows over time if the birth rate exceeds the death rate, or how a radioactive substance decays over time.
Wow. So how about the Newton's law of cooling?
Well, the Newton's law of cooling states that the rate of change of the temperature of an object is proportional to the difference between its temperature and the ambient temperature. Given the ODE is dt over dt equal negative k T minus Ta, where T is the temperature of the object, Ta is the ambient temperature, and K is a positive constant. This is the first order linear ODE. Solved by separating variable and integrating 1 over T minus T0 dt equal negative k dt. Integrating, we find ln modulus T minus Ta equal negative k T plus C. Hence, T equals Ta plus C exponent power negative kt. These models can describe how a hot object cools down to room temperature, such as a cup of coffee left on the table.
Oh, I see. Thank you, Jia Ze. Now, Xuan, can you tell us the uses of ODEs in electrical circuits?
Sure. In electrical engineering, ODEs are used to model the behavior of circuits. Consider a simple RC resistor capacitor circuit. ODE Vt equal to IR plus Q over C, where Vt is the input voltage, I is the current, R is the resistance, Q is the charge, and C is the capacitance. Using I equal to dq over dt, we get Vt equal to R times dq over dt plus Q over C. Solve this first order linear ODE for Qt and subsequently for IT. This model helps us understand how the voltage and current in a circuit change over time, which is crucial for designing and analyzing electronic devices.
All right, thank you so much. So our sessions today has been ended already. In this video, we introduced ordinary differential equations, explore the key concepts such as order, linearity, and initial conditions, and discuss the solution method such as separations of variables and integrating factor. We also demonstrate the applications of ODEs through the example such as exponential growth, Newton's law of cooling, and electrical circuits, highlighting their practical significance. ODEs are vast and fascinating field with many advanced topics and applications. We encourage you to explore further, including studying the higher order of ODEs, system of ODEs, and numerical method of solving complex ODEs. Thank you for watching, and we hope this video has provided you with a solid foundations in ordinary differential equations and inspire you to delve deeper into this important area of mathematics. So goodbye and stay safe.